Okay, so let's start with number 1 on the 2011 FRQ. So pH of solution in beaker 1 is 1. Okay, and hopefully you guys saw that it's this. You're going to use this formula. pH is the negative log of the concentration of H plus. HCl is a strong acid, complete dissociation. So you just plug in 0.1 right here, and that gives you 1. Okay, so now answer part A is 1. Any questions on that one? Okay, let's move on to the next one. Part B1, it's going to be the Kb expression, and you have the reaction right here. So the expression for Kb will be concentration of NH4 plus times concentration of OH minus divided by just the concentration of ammonia. We ignore H2O because it's a liquid. Any questions on that one? Okay, so for the next one right here, part 2, we're going to be using the Kb expression. Now it tells us Kb is 1.8 times 10 to the negative 5. And so we can just plug in the values here to solve for OH minus. Okay, so there are a couple ways you can do this. You can either set up an ice table to figure out what the concentrations are and the variables are. And if you do that, you're going to get x times x, so x squared on the top for this. And then on the bottom, you'll get 0.1 minus x. Okay. Okay, but you don't have to use the quadratic formula because it's negative 5. So we can assume that the change is really, really small. And so you calculate for x, and you should get about 1.3 times 10 to the negative 3 molarity. Okay. That's going to be 0.0013, around there. Okay. Any questions on that one? All right. Okay, let's move on to part C. Now, part C1 is pretty simple. You guys should be able to identify that this reaction right here, the acid reaction, is just the reverse of this one right here. So for this reaction in part C, we can use the Kb from part B. So I'm going to erase this real quick. And then we know that Kw is equal to Ka times Kb. So if we're looking for the value of Ka, it's just going to be Kw divided by Kb. So 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So Ka is 5.6 times 10 to the negative 10. Okay. All right. Any questions on that one?
5.5.
5.5 is, that's fine. Close enough. Most important thing is 5 times 10 to the negative 10. Yeah. Okay, let's go to part 2 of C. Now, this is where I think the problem starts getting a little bit trickier. So it says the contents of beaker 2 are poured into beaker 3. So what we're doing is we're taking this and we're adding it into here. Okay. And then the solution is stirred. So we're going to assume the volumes are additive, and we're going to find the pH of the resulting solution. Okay. So what we want to do is first, what I'm going to do is I'm going to write the equation for what's happening. If you didn't write the equation, that's fine. I'm just doing it just to kind of help me explain what's going on. Okay. So what we're doing is we're taking the contents of beaker 2 and combining them with beaker 3. Okay. So we're basically going to be combining NH3 plus NH4Cl. Okay. Make sense? Okay. Now, they're going to react together, but if you guys kind of take a look at this, we can kind of see already that it's going to dissociate. These are going to dissociate, right? So it's going to be NH4 plus and Cl minus. Okay. So that's going to be the left side of the equation. Okay, so what's happening in this equation right here, and we know that there's obviously water in there as well. Okay, so these are the 4 compounds that are going to be in beaker 3. Okay. Okay, so we know from the equations that we saw earlier that there's going to be 2 things that it's going to be going on. This is going to act as your acid, and this is going to act as your base, right? So there's 2 different reactions that's going to happen. This guy is going to give to water, and water is going to give H to NH3. Does that make sense? Okay, so that's basically what's going on. And so what we figured out earlier is that Ka is equal to 5.6 times 10 to the negative 10. Okay, and if you guys noticed earlier, you got 0.1 molarity of this and 0.1 molarity of that. So the concentration of these two are going to be equal to each other, right? And so if we look at the Ka expression from earlier, NH3 times your acid divided by NH4 plus, okay? We can assume that these two are going to be equal, right? Because it's 0.1 and 0.1, right? Okay, so these guys actually cancel out. And so if we cancel out, we get the concentration of H3O plus, and that's going to be your Ka. Does that make sense? Okay, so let me rewind. Okay, so this part makes sense, right? Where this is what we're combining when we combine beaker 2 and beaker 3. When we combine these things, we know that NH4Cl is going to dissociate into NH4 plus and Cl minus. The important part of this, what's going on here, is going to be between these three. Now, we saw earlier that there's two reactions that can go on. The first one is this reaction right here where NH3 reacts with water. And the second reaction is where NH4 reacts with water. And the only difference is that one acts as an acid, one acts as a base. Does that part make sense?
Yeah.
Yes? Okay. So what we're gonna do is, since the problem is asking us to find pH, right? So negative log of H plus or H3O plus. We basically just need to find the concentration of H3O plus. Okay, now we have the Ka expression. We have the value and the expression for it. And then we see here that it's 0.1 molarity of NH3 and 0.1 molarity of NH4Cl, right? So if we plug them into the Ka expression, we know that these are going to be the same. So these guys will cancel out with each other, which means H3O plus will be equal to 5.6 times 10 to the negative 10. So we just plug it into here. So it'll be negative log of 5.6 times 10 to the negative 10. And so for your final answer, your pH is going to be 9.25. So it'll be slightly basic. Yes.
So I get that.
Mhm.
I did not do that. I got the wrong answer.
Okay.
But can you like explain why my way is wrong?
Okay. What was your way?
So well we found like the like concentration of H plus and the concentration of OH minus from like those two, like, and then we turned that into moles, and then we found a new concentration from the combined volume
How did you find the concentration of H plus and OH minus?
with an ice table, like the values.
I'm gonna have to see your specific. I'm gonna have to see your specific ice table. Was your pH greater or lower than 7?
Ice lower. I got pH of like 5.3.
You might have put the change in the wrong places.
Okay.
Yeah, let me double check yours, but because your KB value is greater than your Ka value, the equilibrium is going to shift to produce more base.
Okay.
Yeah.
I don't know. So I took those concentrations and I found like separately the pH and the OH, and then I just subtracted.
Yeah, I'll have to look at it. I'll look at it after we finish this problem. But yeah, see if the pH is lower than 7, that means you put the change on the wrong side of the ice table. But I'll double check and I'll go over it with you. Okay.
Would that like if I did the math right, would that like process? Maybe probably weird.
So it says in the grading scheme that it's 1 point for recognizing that the concentration of NH3 is equal to the concentration of NH4. So this part right here where they're equal.
So you have to
Yeah. So if you have that on your ice table, then you should probably get a point for that, and then 1 point for the correct pH. So if you were able to identify that the concentration of NH3 and NH4 are equal to each other, that's 1 point. And then the second point is the actual pH value. But I'll double check your guys too. Yeah. Uh-huh.
I found pOH concentration of equation of beaker 2.
Mm-hmm.
I did negative log of 0.00134.
Mm-hmm.
And then once I got 2.87 as effective for why wouldn't
So
that?
you went in the right direction. Because when you mix the solution, beaker 2 with beaker 3, that's because there is going to be a common ion that's going to change it a little bit. I'll have to double check your calculations too.
I think
Mm-hmm. Yeah, I'll double check yours. Yeah. Any other questions? Okay, but pH is 9.25. Yes.
save my question.
Okay. Uh-huh.
But because I thought the numbers from when you've already calculated like
Uh-huh.
so I did it that way and then I got like this answer.
Mm-hmm.
But why does it work both ways? Like why do we use the original calculation at the end? Like the second.
Like why can you use these concentrations? So you're correct in that when they mix together, the equilibrium concentrations will no longer be 0.1 and 0.1 because obviously they're going to react together.
They are react and then you mix.
Well, they're in equilibrium.
Yeah.
So yeah, the reaction is going on, and then when you mix it, it's gonna shift the equilibrium because now they're reacting with each other. Yeah. Yeah, let me double check your paper as well. We'll take a break after we finish this problem, and then that's when I'll go over that. Okay. Yeah. Was your pH greater or lower than 7? 9.24? That's correct. That'll work. So your method works. Yeah. Yeah. Why your method works? Yeah, I'll double check and I'll let you know. But great job. I have no idea what you did, but great job. Okay, let's go on to the next part. So for part D, so in part D, basically you're continuing on with what happens in part C. So part C, it says you mix beaker 2 and 3, and so everything is in here. So we'll say 2 and 3, and we said the pH here is 9.25. Now we know that in here we have NH3 and we have NH4 plus, right? And they're in equilibrium with each other. Okay, so that's kind of where we're going. And then now they're saying you're going to take the contents of beaker 1 and add it to this beaker. So you're mixing all 3 of them together now. And then the question is asking you, is this an effective buffer? Now, it's asking, is it a buffer after once you mix all 3 of them together? Okay, now if you guys remember, a buffer is a weak acid-base conjugate pair, right? So weak acid-base conjugate pair. If you take a look at this is a conjugate acid-base pair. So right now, what you did in part C, what you have right now, this is an effective buffer because it's conjugate acid-base pair. But if you take a look at this is a strong acid. So if you add a strong acid to this buffer, what's going to happen is the acid is going to react with your base. So the HCl will react with the NH3. Since it's a strong acid, the reaction is going to go basically to completion. And so what's going to happen is you're not going to have any more base because the acid will react with all of it. Therefore, once you mix everything together, the only thing that you really have is an acid. And so the answer is no, it is not an effective buffer because the HCl will react with NH3. And the only thing that you'll really have left over in the solution is NH4 plus, which is an acid. Yes. Yes, salt right here. NH4Cl.
Oh,
yeah. And then it's a conjugate of it.
Yeah.
Mm-hmm.
Oh,
okay. So if you said no because you're only left with NH4 plus or something along those lines. Yes. Yeah, it's a little vague. You'll have to be more specific that the HCl will neutralize the base. And that's why the concentration will not be equal, because one of them is 0 and the one is still there, 0.1. So yeah. What's up?
Let's say like only half the HCl was added. That'd be like being effective buffer or like concentration cycles.
Yeah, if it was only half, so you didn't neutralize all of the base, it would still be a buffer. Yeah, because you'll still have some of it, and then chandelier principle, it'll shift to go, to shift it so that it's still a buffer.
Okay.
Yeah. No, because that's an acid. Yeah, the HCl will react with the NH3 to produce, and since it's a strong acid, the reaction only goes one way, right? And it'll produce NH4 plus and Cl minus. The Cl won't want to get together with that. Yeah. Yes. This one, it's 1 point for the correct response and an appropriate justification. So as long as you talked about how that strong acid neutralizes NH3, that's what they're looking for.
No, I totally missed that.
Okay. I'm sorry.
It's okay.
Okay. All right. And then the last one, there are multiple ways to do this. You could use an ice table. I didn't use an ice table, but let me go over the way I did it. But if you get the correct answer, then you're fine. Okay. So last part is you want to calculate the final concentration of NH4 plus. Okay, and so here the key thing to identify is that how many moles of everything are that you've added into the beakers. Okay, so from beaker 1, you can use the molarity formula. Okay, you can rearrange it to find moles, and you should be able to figure out that there are 0.0025 moles of H plus from beaker 1. Okay, beaker 2 is going to supply 0.0025 moles of NH3. Okay, beaker 3 is going to supply 0.0025 moles of NH4 plus. Okay. Now we said earlier in the previous part that these two are going to react together, right? So the HCl, which I'll represent with H plus, will react with NH3 plus, or sorry, not NH3 plus, NH3, and it will form NH4 plus. Okay, everybody good with that? This is what we went over in the previous part. I didn't add the CLs, so if you added the CLs, that's totally fine. And so if you react 0.0025 moles of this and the same number of this, how many moles of NH4 plus did you just make? Yeah, 0.0025 moles from the reaction. However, beaker 3 contained 0.0025. So the total amount of NH4 plus that's in there now is 0.005 moles of NH4 plus. So you could have done it this way. You could have set it up with an ice table. Either way works. But the point is to identify this. And so to figure out the final concentration, you need to use the molarity formula, moles divided by liters. And if you add all three of them together, you're going to have 75 milliliters, which is 0.075 liters. And you should get around 0.067 molarity NH4 plus. Okay, so that one's not too bad. The hardest part was, I think D1 was the hardest question out of all of these. Yeah.
You kind of lost me because 0.005.
So you're good with the beaker 1, 2, and 3. Okay. Yeah, so let's go over it. So we said in the part D1 that these two are going to react and cancel each other out, right? The reason, and so when they react together, this is the reaction that takes place. So this combines with this to make this. Okay, you're combining 0.0025 moles of this guy and 0.0025 moles of this guy, right? So if you combine them together, you make NH4 plus. Yeah. So since it's a 1-to-1 ratio, that means you're going to make the same amount of this. So that's why 0.0025. And then beaker 3 already had NH4 plus. You just made this much NH4 plus. So if you put them together, that's where the 0.005 comes from. That's correct. Yeah, makes sense. No. That we divide at the very end. Make sense?
Yeah.
All right, cool. Alrighty, guys. That's gonna be the first. Yeah.
I don't know what the points like work out for that.
This one?
Obviously the last few.
It's 1 point for figuring out 0.005 moles of NH4 plus, and then 1 point for figuring out that or figuring out the final concentration.
Well, like over the whole thing.
The whole thing.
Yeah, like
5, 6, 7. It's 10 points. 1A is 1 point. 1B is 1 point. Or sorry, 1B1 is 1 point. 1B2 is 2 points. C1 is 1 point. C2 is 2 points. D1 is 1 point, and D2 is 2 points.
what's I don't know like number. Like what's
Oh, yeah, like how, yeah, like.
It's that percentage range that I gave you last time. It changes a little bit every year depending on how it curves. I'll post it on Canvas for you guys. I'm good. I like my voice better. All right, so let's go to number 2, guys. Number 2, the first part is pretty simple. We did a bunch of this before, so this is another dilution problem, which you guys love. And what's the formula for dilution? Yes. Susie got overpowered by all that energy. So yeah, you just need to plug in the values and make sure you keep track of it. But the volume that you need, either V1 or V2, depending on how you plug it in, should be 19 milliliters. Okay. So you need 19 milliliters of your 16 molarity HNO3 to make your 50 mils of 6 molar HNO3. Okay. Make sense? All right, so that one's pretty easy. Okay, step 2 were the procedures. Okay, and the procedures here, I think we did this last time too, so shouldn't have been too bad. But you write the steps for an appropriate safe procedure for making the one that we talked about in part 1. So I'm gonna just type it. Again, it doesn't have to be exactly like this as long as you hit the main point. Okay. Now if you take a look at this problem, it gives you some equipment that you're gonna use. It gives you the safety equipment. God bless you. Okay, and so you gotta involve those. God bless you. Okay, so you can just say something like wear goggles, gloves. Obviously, you want to write complete sentences on the AP test, but you get the general idea. Okay, step 2, you're gonna write use the 100 milliliter graduated cylinder. Okay, to measure out 19 mils of your 16 molarity HNO3 solution. So here we're not using a volumetric or anything like that. We're using the graduated cylinder. And again, it's because if you look at the problem, that's kind of what they're giving you. So you're using whatever's on the problem. Okay, step 3, since you get 2 cylinders, you can write that you want to measure out the remaining amount. So you would just do your 50 minus 19. So you can write down, use your 100 mil graduated cylinder, measure out 31 milliliters of distilled water. That's the size of the graduate cylinder that we have.
Like you can't just pour the water.
No, because the beaker is not a good way to measure, or the measurement here is you need to measure 19, right? And if you look at the beaker, it's plus or minus 10.
No, but you can't use the like can't pour the 19 milliliters into the beaker and then fill the beaker.
Oh, that works too. Yeah, you can do it. So you're saying add the whatever you measured out first and then measure it again in the same one. So yeah, that does work out, but you have to do it in a very specific order then. And that's the part I was going to get to. And this is the part we didn't, this in your reading, but we didn't really talk about it in class. The most important thing here is that you want to add the water first. Okay. Add the water first to the beaker. Okay. Then add your acid to the water. Yeah. So if you, Josie, if you wrote, measure out distilled water, add it to the beaker, measure acid, add it to the beaker, that's fine. But if you did it the other way, then it wouldn't.
Okay.
Yeah. But yeah, good question. You have to add water first.
Why
Yeah.
not?
It's because of the heat of the reaction. If you have something more concentrated, you want to raise the concentration of the solution. You don't want to drastically lower it quickly. Yeah. Yeah, always want to add the water, acid to the water. Yeah.
If you add water and then more water, like just like.
Yes, if we are using the volumetric, but here we're using separate graduated cylinders. And so you just have to add them all at the same time. Yes.
When they give a list of like what you're provided, what's the you?
Try to use as many as you can. But if they're don't use stuff just for the sake of using it.
So also for those ones, we just put like 1, 2, 3, like step 1.
Yeah.
Okay. And then we'll-
Sorry, Susie. Yeah.
Questions?
Same question. Okay, for sure. And then last thing, obviously stir. Yeah. Okay, so that's the general steps. Again, it could be there can be a little bit of variation. The key thing here, as I take a look at the key, is that you want to add, this is the thing that they're looking for, add acid first. Yeah, water second. And then the other point was right here, 31 mils. Yes, water first, acid second. Acid to the water. Yeah. Yes. That works as long as you specify that the water is in the beaker already.
Adding acids to the
Not in a beaker because there's no 50 milliliter line.
oh,
Yeah, the lines, the margin of error is plus or minus 10. So if you look at 50, it could be 60 or 40 in a beaker.
okay.
Yeah, that's why these plus or minus is important. All right. Okay, let's go to the next one. And speaking of the plus or minus signs, number 3 is asking you, why is it not necessary to use a volumetric flask? Why can we just use graduated cylinders? And the answer is really simple. If you take a look at the calculation, how many milliliters of the 16 molar solution do we need? We need 19, right? It's not 19 point something. The last number that we really need to look at is in the ones place, right? And so we can just use the graduated cylinder because if you look at the graduated cylinder, it's plus or minus 1, right? And so we can just use the graduated cylinder. We don't have to be that specific.
But when I got like the basic calculations, I got like 18.75. But then I got to
Then it's sig figs. Yeah. Well, it tells you here that your equipment that you're using is plus or minus 1, so you can round up to the closest ones
Okay.
place. Yeah.
I figured out number 2 again.
Uh-huh.
If it was a solid instead of an acid, that might be wrong.
Solid instead of an acid, the powder.
Yeah.
There's no acid powder.
No, I mean like not like in this like
Uh-huh.
like if you had it at like
Oh,
a solid.
yeah, that means you add a little water, then you add all the solid, and then you fill it up to the line with water.
So can we do the same thing here? Just like the same, like add a little water.
And then add the acid and then add more water. Yeah, you can do that too. That works. The key is add the water first. Yeah. All right. Okay, let's move on to the next part 4. It tells you that the student is going to spill some of the 16 molar, which is pretty bad. That's pretty strong. And then it gives you 3 different solutions that you can use to clean up the mess, the spill. Okay. The one that you want to use, and I'll just give you guys the answer right away, is going to be the NaHCO3. Okay. Because let's think about all the options. You got 16 molarity, HNO3. If you just add distilled water, it's not going to react, right? You're just diluting it, but you're going to dilute it pretty slowly because you'll need a lot of water to neutralize the HNO3. It's 16 molar. Okay, so distilled water is out of the question. Okay, the saturated bottle of NaCl isn't going to work because if you take a look at HNO3, what type of acid is this? Strong acid, complete dissociation. If you take a look at NaCl, what type of electrolyte is it? Strong, yeah. And if you remember your solubility rules, let's say we react this together. Okay, it's not really gonna form anything. It's not gonna form HCl because that's a strong acid. And you're not gonna form NaNO3 because remember this Taylor-Swift is not gonna get together with anything. And so neither of these are going to form. They're both gonna be ionized still. So this guy is not gonna do it. This guy is not gonna do anything either. So by process of elimination, this is the only one that will work. And if you want to get very specific, this is gonna dissociate into Na plus and HCO3 minus. This right here is going to react with the hydrogen. And then that's how it's gonna clean up the spill. Okay. Yeah.
Like, you just said, like, the NA, like, you have to, like, explain the reaction.
No, you can just say that this ion will neutralize it. This ion acts as a base,
Right.
something like that. Or you can say that the explanation that I gave for why the other two won't work, that works as well.
That's fine.
Yeah. One or the other. You don't need all of what I just said. Yeah. So if you want to be very simple, you can just say HCO3 will neutralize the acid, or you can say distilled water will just dilute it, and NaCl will not react with the HNO3. So that works too. Okay, let's move on to part B. Part B is super simple. You want to calculate the moles of AgCl precipitate collected. So basically in this process, what they're saying is, the person made the precipitate, and then first that person dried it, and they dried it again. And then here, the third time they dried it, there's not a big difference between the second and the third. Okay, and so there's probably not much water left over. So this is the value that you want to use for your precipitate. So all you got to do is this number. So 29.2598 minus the filter paper. Where's the filter paper? Right there. 28.7210. That's going to give you a value of 0.5388 grams. And then you just multiply it by the molar mass of AgCl, or divide it, sorry. So you're going to divide by 143.92. And that will give you a final answer of 3.759 times 10 to the negative 3 moles. And then this right here is the molar mass of AgCl. Right. So that's part B. All right. Okay, and then last part for part C, what we're gonna do is we're gonna take our moles right here of AgCl. The alloy that we were separating contained copper and silver, so we can identify that you're gonna have the same number of moles of silver, right, inside AgCl. And then all you got to do is this time you're going to multiply it by the molar mass, 107.87 grams of Ag. Okay, and that'll tell you that there are 0.4 grams of Ag inside that HCl. Okay, then you're just going to divide it by the total mass of the alloy. So 0.4 grams of Ag. The total mass is 0.6489 grams total. And then you just multiply that by 100%, and your final answer is about 62.5% Ag. That's it. Yes.
We solved it by figuring out like the mass of like 1 mole of Ag divided by 1 mole